Hi. So in the last video, basically we talk about what is called the one-tailed test. So usually the question will tell you which direction that you want to test. For example, if let's say this is your bell curve. So usually let's say your significance level is over here. So this is your critical region. So this will be a right tail test. So this part will be 5%. Or the other way around, it can also be left tail test. So if that's the case, this will be your critical region, and over here this will be 5%. So the direction depends on the question. So you need to read your question carefully. There's another type of test called the two-tail test. Whereby in this particular scenario, let's say this is your bell curve. So if let's say you are doing 5% significance level, you will need to separate out half. So two-tailed test basically tells you that let's say you are doing 5% of significance level. So then on the left and on the right, you have to test. So this particular critical region on the left will be at 2.5% of significance level. On the right, it will be also 2.5% significance level. So the middle will be your acceptance level. So whenever you see something like they didn't tell you the direction of your test, for example, so usually for one-tailed test, your null hypothesis will be, let's say something p equals to, okay, let's say your mean equals to some value, and then your alternative hypothesis will be either greater or smaller. So the direction of is either greater or smaller for your alternative hypothesis. That tells you which direction you need to test for your one-tailed test. Whereas for a two-tailed test, usually you will need to formulate your hypothesis as follows. So your null hypothesis will be mu equals to p, and then your alternative hypothesis will be just inequality. So there is no greater or smaller. It doesn't tell you the direction. So when you see this particular scenario in the question, basically what you need to perform is two-tailed test. So now let's look at one example of two-tailed test. It is claimed that 80% of the Americans believes in horoscopes. Medicine doubts that the claim is correct. So if you read the question, so she basically doubts whether it is correct or not. She does not tell you whether this particular claim is greater or smaller. So you are using 10% of significance level and write down two hypotheses, write down the random variables, blah blah blah. So you can let x to be the number of people who, or specifically Americans in this particular scenario, who believe in horoscope. So then she asked 16 Americans. So immediately you know that this is a binomial distribution. The n will be 16 and your probability of success will be 0.8. So now you need to formulate two hypotheses. your H naught would be to say that your probability P equals to 0.8, because it doesn't tell you the direction and you want to perform two-tilt tests. So your H1 should be P not equals to 0.8. Notice a difference between the two-tilt test for the alternative hypothesis versus the one-tilt test ones. So you know that your significance level is 10%. Okay. So given that 50 of the people believe in horoscope, what is the critical value? So now P, okay, Px greater or equals to 15. So over here, I'm basically performing something like this. So this is a two-tilt test. You can either do it like this, so this is P x equals to 15 plus P x equals to 16, and this is 0.1407. You can actually calculate that one. So Px equals to 15, so it's 16C15 times 0.8 power 15 times 0.2. So the left side will be 0.1126. The right side, the 16 one will be 0.0281. So this sums up to 0.1407. So remember that when you perform two-tilt tests, because it's 10%, so you divide by 2. So over here, you need to have only 5% or 0.05. The other side is also 0.05. Sorry, 5%. So you determine the critical region over here should be 16. Because if n equals to 15, basically this is greater than 0.05. So if Px equals to, greater or equals to 16, then this is 0.0281, which is smaller than 0.05. So on the right side, your critical region will be at n equals to 16. So you can also test on the left side, let's say 1. So this is 0 and 1. So the first one will be 16C0 times 0.8 power 0 times 0.2 power 16. So it's a very small number. So almost equals to 0. Then you can calculate the other one. I suppose the number can be larger. Let me do some rough estimation. So let's try up to 5. Yep, it can definitely be larger. So apparently, roughly speaking, just by doing some estimation, I think you can take it to 9. So it's kind of a complicated process if you want to sum them all up. So I won't bother to write it down. Okay. So what I can do is to calculate everything out. So you need to give me some time. So I calculated 9876. And then 5. Okay, so I have a rough estimation number. So this is just an estimate because I don't want to waste all the time just to calculate this. This value should be very close to 0.0227, for example. Let's put it 0.03. It should be very close to 0.03, which is 0.0 less than 0.05. So the way I do this is quite simple. Basically, you just test px equals to. Okay, so how do I get the rough estimate this number? So first you find the mean, n times p, which is, so n is 16, p is 0.8. So this is around 12.8. So it means that your probability distribution is not really symmetric, but is skewed to the left. So it looks something like this. So it means that you need to achieve quite a large number of n before you can reach to your significance level, which is 0.05. So in this case, you can start with the testing px equals to 10, and you can calculate 16c10, for example, 0.8 power 10 and then 0.2 power 6. So if you calculate this is 0.055. So this is definitely greater than 0.05. So definitely you want to start with x equals to 9, for example. So if you start with x equals to 9, you can find that it is around 0.01965. So if px equals to 9, this is 0.01965, which is less than 0.05. So definitely you want to start with n equals to 9, for example. So if you calculate everything out, then you find that on the left, your critical value will be n equals to 9. So those are your critical values. So now you have 15 people. So your critical value is 9 and 16, and your n is 15. So do you have any evidence to reject the claim? No, you don't. So you don't have sufficient evidence to reject the claim, since, sorry, I don't have space to write, so I will write down here. So you have insufficient evidence to reject the claim, since I might as well move the sentence down here. Since px greater or equals to 15 is greater than 0.05. Okay. So for this particular set of answer, I write down the two hypotheses, and then I calculated the critical value, and finally I tested the claim. So these are the three important things that you need to do in this particular subsection. Okay. So now let's look at part B. She conducts a large survey, asks 160 Americans if they believe in horoscopes, define the distribution. So this is part B. So X now is a binomial distribution with 160 people, and your probability of success is 0.8. But the question asks you to use a suitable approximating distribution. So it means that you need to approximate using normal distribution. So of course you can proceed to test whether or not this satisfies your condition. 160 multiplied by 0.8 is 128. And Q would be 32. Both are greater than 5, so definitely you can use normal distribution to approximate your binomial distribution. So the mean would be n times p, which is 128. The variance will be npq. So you have 128 times 0.8 times 0.2, which gives you, sorry, not 128, but 160. So it gives you 25.6. So now you are required to do a 5% significance level, write down two hypotheses, and then test the claim. So, okay, you have H naught, which is P is given by 0.8, H1, P is given, sorry, P is not 0.8, because this is a two-tail test. And your significance level This time, remember, this is 5%. So this particular question, they did not ask you to find the critical values. So you don't need to find the critical values. You just need to test the claim. So if you are performing a two-tailed test, you need to test from the left and test from the right. Either one of the test statistics fall into your critical region, then you reject your hash knot. So this is something important that you need to remember. If the calculated test statistics falls into the critical region, then your hash knot is rejected. So you need to do the left and the right. Either one fails, basically you fail. So let's look at px greater or equals to 116. Because you are doing approximation, so this will be 115.5 minus 128. Remember that you need to minus 0.5 for that particular value. And then this is 25.6. So when you calculate this, this is given by that. And this value is the same as this value. Finally, read from your table. This is 9932. Okay, so the right tail is, if you just base on the right tail, basically you don't reject the claim. So now let's look at the left tail. So this will be pz smaller or equals to 116.5 minus 128. Then you divide the whole thing by 25.6. So this is pz smaller or equals to minus 2.273. So because of the direction, this is 1 minus pz smaller or equals to 2.273. And finally, you get this. So this actually falls into your critical region because px smaller than 116. This particular probability is smaller than 0.025. Therefore, you have, so medicine has enough evidence to reject the claim. So write down what is hash knot. Hash knot is saying that 80% of Americans believe in horoscopes. So write that particular sentence down. Over here, I just want to save space, so I didn't write it down. So that is two-tailed test. The final section of this particular chapter teaches about the type 1 and type 2 errors. So because this is the whole hypothesis testing is just a statistical test, there are probability, there are chances that you might accept the wrong hypothesis or reject the correct hypothesis. So if you look at the table, for example, the null hypothesis is true versus the null hypothesis is false. So really you have 4 different scenarios. Let's not draw this first. So the first one is you accepted hash naught, and then you rejected hash naught. Perhaps I can draw this. So if hash naught is true and you accepted the null hypothesis, then nothing is wrong. You are doing the correct choice. But if hash naught is true and you rejected the hash naught, this is what we call as the type 1 error. And usually we also call this false positive. So now if you have a false hash naught and you accepted it, so this is what we call as the type 2 error, and this is sometimes also called the false negative. So finally, if hash naught is false and you rejected the claim, then you are doing the correct choice. So one of the very important questions in this particular section is to calculate, for example, the probability of performing your type 1 errors and type 2 errors. So before I proceed to that, remember that for type 1 error, so usually for type 1 error, the probability will be equals to your critical region. If let's say you are doing a discrete distribution, discrete random variable, discrete probability distribution, if you are doing continuous random variables, then usually the probability of performing type 1 errors will be your significance level. So for type 2 error, you need to take the assumption that your hash naught is false. Usually when they ask you to calculate type 2 errors, you must have the test statistics of when hash naught is false. You need to have this particular test statistics before you can calculate the probability. So the probability for type 1 and type 2 error is basically like this. Probability of, let's just write this. Probability of type 1 is just your conditional probability of reject hash naught, provided that hash naught is true. The probability for type 2 error is just the probability of accept your hash naught, provided hash naught is false. So now let's look at 2 examples to calculate the type 1 error and type 2 error, the probability of it. So the first question, supplier of duck hatching eggs claims that up to 80% of the duck eggs will produce the ducklings. So Gareth orders 16 duck hatching eggs and carry out the hypothesis test. Define the random variable and the parameter. So the random variable would be the number of duckling hatch. So this is a binomial distribution. You have 16 eggs and the probability is 0.8. So these are what you need to define. State the null and alternative hypothesis. The null hypothesis will be this one. So you are testing with so this one here you need to determine whether or not this is a one-tailed test or two-tailed test. So up to 80%. So it means that this is a one-tailed test. So these are your null and alternative hypotheses. Find the rejection region. You can test px greater or equals to 15, for example. So this will be px equals to 15 plus px equals to 16. When you calculate this, this is 0.1126. The other one will be 0.0281. So this is 0.1407. You just want to find the rejection region. So this is a two-tailed test. Sorry. This is a one-tailed test. So your significance level is 10%. Okay. So when x equals to 15, this is more than 0.1. And then when x equals to 16, this is less than 0.1. Therefore, the critical value will be 16. So basically, you have something like this. You can draw all the bars, but basically you have something like this. So let's say this is 15. Okay, you know what? So let's say this is your 10% of your significance level. Your x equals to 15 bars, kind of like halfway in between. So that's why the rejection region will be at 16. The critical value will be at 16 because this is a discrete random variable. So then what is the probability of type 1 error? So just now I mentioned that if it is a type 1 error, if it is a discrete random variable, then your type 1 error, probability of type 1 error would be just your critical region, the probability at your critical region, which is px equals to 16, and this is 0.0281. So you can try to define what is a type 1. So let's say if I ask you what is the type 1 error in this context. So the test that you perform is to test whether or not it is more than 80% of your duck egg will produce ducklings. So remember that type 1 error is your hash not is true, but you rejected it. So it means that you have less than 80% of the eggs will hatch, but your hash node is falsely rejected. Which means that by right you have less than 80% of eggs that will hatch. But since you rejected your null hypothesis, so it means that you wrongly thought that you have more than. So this is falsely how should I write it down? Falsely concluded that more than 80% of the eggs will hatch. So this is type 1 error. So now let's look at the final question on type 2 errors. So basically this one I think contains type 1 and type 2 errors. A gardener knows from experience that the height of the sunflower is normally distributed with mean 1.8 meter, standard deviation 0.32. So a friend claims that if you sing, the sunflower can grow taller. They decided to test the claim. So one plant will be sung each day while it grows. State the null hypothesis and the alternative hypothesis. So your hash node is basically the mean height is 1.8 meter. Your H1, because growing taller, so it kind of tells you the direction. So this is basically a one-tail test. So, alright. The gardener will be convinced that singing increases the sunflower height if x is greater than 2.25. So in this particular case, they did not tell you the significance level. So then your type 1 probability will be just the probability of x greater than 2.25. Because this is a continuous distribution, if let's say they tell you the significance level, let's say your significance level will be 5% for example, then you don't need to calculate anything. 5% will be your probability of performing your type 1 error, because this is a continuous random variable. So which is why they did not tell you the significance level, because they want you to calculate this. So convert this into the z-score. Because this there's no approximation, so you can just safely convert it. The mean is 1.8. Standard deviation is mentioned to be 0.32. So this is pz greater than 1.406, or this is 1 minus pz smaller than 1.406. So you can calculate this one out. Find from the table, you get 0.08. So that will be your probability of type 1 error. So what is your type 1 error in this context? So let's say I ask you what is a type 1 error in this context. So your plant does not grow taller after you sing every day. But it is falsely concluded that the plant will grow taller if you sing every day. So this is a type 1 error in this context. So the friend says that the mean height is 2.4. Assume the standard deviation is the same. Calculate the probability of a type 2 error. So this is what I meant by you have a different test statistic if you were to calculate your type 2 error, because originally your x is normally distributed by your mean, which is 1.8, standard deviation is 0.32. So this is the test statistics for H0 is true. So now you have a different test statistics. This is 2.4 and then 0.32 square. So this is a test statistics for when your H0 is false. So now you can calculate your type 2 error. So remember that for type 2 error, basically what you need to calculate is you accept your H0 provided that your H0 is false. So if you use this particular test statistic, basically you fulfill the condition. So now you need to define what do you mean by H0 is accepted. So this basically means that your x has to be smaller than 2.25. Why 2.25? Because when your height is greater than 2.25, then you have evidence saying that singing does makes your sunflower grows taller. So you want your H0 to be accepted, meaning that you don't want it to be grow taller. So that's why you need it to be smaller than 2.25. So convert to Z score. This is 2.25 minus 2.4, which is your mean for this particular statistics. Sorry, there's no square root. It's just 0.32. Did I write the right thing? Yes. So this is PZ smaller than minus 0.469, and it is 1 minus PZ smaller than 0.469. So find out the value. So this is 0.3196. So this is a probability of type 2 error. So in this context, what is your type 2 error? So it means that your plant grows taller, but it is falsely concluded that it does not grow taller. So that's what it means by a type 2 error in this context. So that's how you calculate your probability for type 1 error and type 2 error respectively. That's all for this chapter. Thank you.